Continue with lesson number 9, laws of motion. So far, do you find any problem till yesterday? So far, I'm talking about.
No, ma'am.
No? We finished this also, I think so. Inertia of rest.
Yes,
Remember? Right?
yes.
Okay. Now, another examples of inertia. The one we had already done. Detailing we will do now. So this is what we did activity yesterday. You will flip the card and the coin will fall inside the cylinder, right? Or inside the glass. Am I right?
Yes.
So this is what inertia of rest. Okay. Now you will read where we are seeing these examples. We'll do one by one. Please start with it.
A passenger in a bus jerks backward when the bus starts suddenly because the passenger tends to be in inertia of rest, whereas the bus is moved away forcefully.
That means have you experienced this anytime? That when you are traveling in the bus, you are seated. You are not moving. Is it right? You are not moving. You are
Ye-
seated on a seat, right? When bus starts suddenly, when it starts to go forward, suddenly you go backward. Am I right? Am I right?
Yes, ma'am.
Because you have the inertia of rest. You are at rest actually, but you also get into motion because the bus is also in motion. You understood? So this is one
Yes, ma'am.
inertia of rest. Okay. Second one.
When a bed sheet is flicked away suddenly, dust particles fall away as they tend to be in
Hello.
inertial of rest.
Fine. Same way, when you suddenly, it should be the motion should be very fast. Then and then only you can see the inertia of rest. The second example is that you just take away the bed sheet. You're removing the bed sheet from the bed, and suddenly you can see the dust particles. You can see literally the dust particles falling away. Why? Because dust particle was in the rest. So you can see dust particles showing the inertia of rest. You understood now? Here, what is moving? The bed sheet. And what was at rest? Dust particles. You understood now? Hello.
Yes.
Yes. Third example, beta.
When a branch of tree is carrying a mango is suddenly flipped, mango falls off due to inertial of rest.
Same thing happens with a mango tree. So a branch, you just tap the branch and the mango falls down. You must have tried so many times, isn't it? Either you hit the mango with a stone or you just shake the branch. Have you ever observed that? When you shake the branch, the mango falls off. Yes or no? Mango was at rest, but due to the movement of the branch, the mango falls down. Am I right? Am I right? Boys, 9th standard boys, do you understand what I'm saying?
Yes, ma'am.
Yes? Okay. So in the first example, passenger inertia of rest. Second example, dust particles inertia of rest. Third example, mango inertia of rest. Do you all agree with me?
Yes, ma'am.
Okay, fine. All of you understood, I hope? Okay. Some more examples. We'll not do the first one because it's been repeated. We'll do the second one. But the first one we have already done it. Okay. So now we will do some more examples of inertia. Please start.
An athlete after
Athlete.
reaching the athlete.
Athlete.
Yes, athlete after reaching the finishing point cannot stop suddenly, or if he stops suddenly, then he falls toppling head down.
Have you observed this? If
Yes,
you
ma'am.
run, I'm talking about you people, if you run very fast, you have to stop at certain point. If you try to stop yourself, you will fall down with your head down. Have you ever tried? So what we do, we don't stop suddenly, but we keep on reducing our speed, isn't it? And after finishing the race, we keep on moving. We keep on running with a slow speed. It's it's the daily observation. That's what we do, right? Isn't it?
Yes, ma'am.
Yes. Okay. So never try to stop at the finishing point. You will fall down. Third,
A car takes some time and moves through some more distance before coming to rest even after the application of brakes.
is it true? You apply brake to any vehicle, it will not stop there, but it will keep on moving to a certain distance. Have you observed this in your bicycle, in your scooter, or in your car? If you apply brake, it doesn't stop at that time, but it reduces speed and it goes to the forward direction. Yes or no? Ninth standard, I'm addressing you better. Yes? Do you agree with me or not? If you have any dilemma, if you have any doubt, please ask me again and again. But don't be quiet. These are the examples. This is daily to daily activities. Remember better. All these activities we are following every day. So, do you agree with me for this the third case?
Yes, ma'am.
Yes. Okay. Now the fourth one. Start.
A rotating fan continue to do so for some more time even after the current is switched off.
Is it right?
Yes, ma'am.
Okay. Fifth.
An oscillating simple pendulum bob does not
Sorry, halt.
halt at the mean position, but continues to move further.
Now this is the pendulum and this is the bob. This is the bob. Okay. Now it doesn't stop here. Pendulum, then it goes here, then it goes here. Yes? Am I right? You get in the clock, the wall clock, you've got pendulum. Yes or no? So it does not
Yes,
stop here. It does not stop here, but it keeps on moving here, then it keeps moving there. Like this, it keeps moving. Right? It does not stop at the mean position, but it keeps on moving. So this is another rest of inertia. Next,
when a car or bus turns around a sharp corner, we tend to fall sideways because of our inertia to continue to move in a straight line.
okay, my car was moving in a straight line, right? Just imagine the car, your car, my car, our car is moving in a straight line on a straight road, on a highway. Then it comes, it curves. Then the road turns. And when it turns, when the car turns, we are pushed onto the door. Yes or no?
Yes.
Right? So that is due to mass of inertia. Sorry, that is due to inertia at rest. We were at rest, but we are pushed onto the side, onto the door because of this case, because of this condition. Because we are moving in a straight line and now we have taken a curve, taken a sharp corner, and we fall sideways towards the door. And we think that we will come out of the car, isn't it?
Yes,
Hello?
ma'am.
Yes? Okay. The last one, please.
It is dangerous to jump out of a moving bus because the jumping man's body is in the state of inertia of motion.
Inertia,
But
beta.
inertia,
Inertia. No, it is inertia.
inertia of motion, but the legs are suddenly stopped by the ground and hence he topples down.
Have you ever tried? Never ever try. Never ever try. Because see, we jump. My body was at motion earlier because I'm in motion with the bus, isn't it? But when I jump, my feet gets grounded by the ground. It doesn't allow me to move, but my body is moving. And what happens? I fall down. You understand? My leg is not moving, but my body is moving. So I fall down. You got my point?
Yes, ma'am.
Some more examples of inertia, please. Yes.
Example of inertia. If a striker hit
Striker.
a spy,
It's a striker.
if a striker hit a pile of coin on a carom board, the lowest coin moves out and due to inertia of rest, the other coin fall down.
Is it true?
Yes, ma'am.
Yes. Second,
If a coin placed on a playing card or a tumbler is flicked with the finger due to inertia of rest, the coin falls down into the
that we did
tumbler.
yesterday. Yeah, into tumble. That we did yesterday. Yes. The activity.
Yes.
Okay. Third,
When we travel in a car and the driver applies the brake suddenly, we tend to fall forward due to inertia of motion.
this also you agree?
Yes.
Okay. Fourth,
When we are standing in a bus and the bus begins to move suddenly, we tend to fall backward because our feet in contact with the floor moves toward, but the upper part of the body continues to remain at rest due to inertia of rest.
you understood? That
Yes.
my feet, our feet in the bus is in motion. Yes? But the
Yes.
upper part of the body is at rest. So we fall backward. You got my point? When the bus starts, when we are standing. Okay? Any problem? Any
No.
problem, beta? These are all examples of inertia of rest. Now we will have a comparison. We'll see what is the comparison between inertia and mass. So we all have come to know about inertia nicely. Do you have any doubts regarding inertia?
No.
This is a topic, it's a new topic, so that's why I've taken so many slides to explain to you. Someone's mic is on, beta. Okay, start.
A body at rest continues to be at rest, and a body in motion continues to be in motion. This property of a body is called its inertia.
So we are well aware of this definition of inertia. This is the second time we are doing the definition. We are aware of this definition, beta. We know what is inertia.
Yes, ma'am.
Yes? Okay. Begin, beta.
The inertia of a body is measured by the magnitude of force required to change the state of the body. The force required to change the state of a heavier body is more than the force required to change the state of the lighter body. This is because the mass of the heavier body is more than the mass of the lighter body.
So, so, continue, beta.
Yes, ma'am. So, the mass of the body is a measure of its inertia.
So it is directly proportional. Mass, inertia. More mass, more inertia. Less mass, less inertia. What do you say? We read out all the things. The second stanza, it has got how many lines? Almost 6, 7 lines. But what it What is the conclusion? What is the summary of this? That mass is directly proportional to inertia. If it is more mass, inertia will be more. Less mass, inertia will be less. Did you understand?
Yes, ma'am.
That's it. That's all you have to remember. You can see over here, this is more mass on the left one. This is left one and this is the right one. This is more mass. So mass is more mass. So more inertia. This is less mass, so less inertia. Is it clear? Is it clear?
Yes, ma'am.
Now we come to another topic. The next topic is momentum of a body. Momentum is velocity. What is required? Velocity is required. That is called as momentum of body. This is totally new topic. Okay? Please start.
The momentum of a body is the product of its mass and velocity. Momentum is equal to mass into
Momentum.
velocity.
It is momentum.
Yes, momentum. P is equal to mv,
So
where
what is
P,
momentum? It is P, right?
yes, where P is the momentum of a body, m is the mass of the body, v is the velocity of the body. If a body is at rest, its velocity is zero, and so its momentum is also zero. The SI
Just
unit of
just a moment, beta. P is equal to mv. The body at rest, that means V is equal to 0, right? So you multiply anything with 0, it becomes 0. So P is equal to M into 0. So it becomes 0. So momentum becomes 0. Is it correct? Do you agree with me? Hello,
yes, ma'am.
boys. Huh? Okay.
The SI unit of momentum is kilogram meter per second or meters per second or kg meter minus वन. इस वो क्या आता है मीटर स्क्वायर
Yes?
वो
No,
एम
it
एस
will not
माइनस
come
वन
meter square. No, it cannot come as meter square, beta. I will show you how.
मीटर
Mass
पर
is always, it is meter per second. Meter per second square is for acceleration. Yeah, velocity is meter per second and
yes
acceleration is meter per second square. Don't confuse, okay? Now
yes
you understood better? Okay, fine.
yes
So here is kilogram. Please put off someone's mic is on. I can get my voice back. Thank you. Now M is kilogram. V is meter per second. Got it? This is what you got. What do you see? M is kilogram. V is meter per second. This is the unit, right? And if you take S on top, it becomes S inverse, right? You can see over here S inverse. See, got it?
yes
Second
ma'am.
inverse. Okay, fine. Continue better.
Example: a truck a truck moving at a very low speed can kill a person standing in its path because of the heavy mass of the truck.
You understood now? Now, if a truck is moving at a very high speed, then also it can kill the man. If the man, because of the speed, you got my point? So, man can be flung. The man may not come under the truck, but he can be flung by the speed of the truck, and he may break his bones, or he may have hemorrhage, or he may die. In both the cases, that person may die. But when a truck, what it's trying to suggest is, but when a truck is going at a slow speed, then and then also it can kill a man. You got it?
Yes, ma'am.
Okay, why? Because of the mass. Now, what are we considering right now is the mass of the truck. Mass of the truck is massive. It's huge, isn't it? And a man mass or the weight could be just 70 or odd 60 to 70 kg, and the mass of the truck is in tons. So obviously we will die, right? So now we are considering mass only. Let's take the second case.
A bullet of a small mass, when fired from a gun, can kill a person because of the large velocity of the bullet.
This also you agree? Bullets are so small, don't you think so? They're so small. How can they kill a person? Same thing, the impact. Because that bullet is fired with a high velocity. And when the bullet gets inside the body, it makes a hole. Because of the motion of the bullet, it's going round and round, it makes a big hole. See, it enters the body, but when it comes out from the other side of the body, it makes a big hole inside. And that's why the person dies. You understand?
Yes.
It makes a big hole inside the body because of the movement of the bullet. Okay. So, the last line, beta.
So the impact of a body depends upon its mass and velocity.
So, we have understood in the first case, the truck, we are talking about mass. In the second case, bullet, we are talking about velocity. Did you understand?
Yes.
So, what are we talking about? Mass and velocity.
Velocity.
Understood nicely? How we are coming to conclusion? 9 boys.
Yes, ma'am.
All of you understanding what are we trying to get at?
Yes.
Yes. Okay. Again, the same thing. You will let me know. Fazil, is that you who is reading?
No, ma'am.
Then who is it? Who is reading, beta? Abdul.
Ma'am. Yes.
Okay. And Abdul, so you will let me know. See, momentum, we read it earlier. Again, we are going to read momentum. You will let me know what extra information this slide gave. Okay? Abdul?
Yes.
Okay, beta. Let's start.
Momentum is the quantity of a motion in a body and it depends on its mass and velocity.
We agree?
Yes.
Okay. Second.
Momentum of a body is defined as the product of its mass and velocity. For
That
example,
is. No, it is
that
that is.
yes,
It's not example. Yes.
yes, that is momentum is equal to mass into velocity or P is equal to m into v.
This also we agree?
Yes, momentum is directly proportional to mass. If a cricket ball and a tennis ball move with the same velocity, momentum of cricket ball is more because its mass is larger than that of the tennis ball. Moment,
Okay. Is it
yes,
okay? Just a moment, beta. Is it okay? You agree? So what new information we got? This one.
yes, the cricket ball and tennis ball.
Yeah. And the momentum is directly proportional to mass. This is what was not written, but I told you.
Hmm.
Here it is written. That is what extra information you got in this slide. Is it okay?
Okay, ma'am.
So what
Momentum,
we just a moment, beta. What we saw, first one, this is first one. Momentum is directly proportional to mass, and we gave the example. Now, what we are going to see, second one.
momentum is directly proportional to velocity.
So you understood now? So momentum is directly proportional to mass and velocity. You got this information in this slide?
Yes, ma'am.
Okay. Next, let's see the example.
If two cricket balls move with different velocity, then the momentum of the ball with greater velocity possesses more momentum.
You agree? So more
Yes,
velocity, more momentum, right? Okay. Then
if a body is at rest, its velocity is zero and hence its momentum is zero.
We know this.
Yes,
Then,
but every moving body possesses momentum.
right?
Yes, momentum is a vector quantity.
You agree? It
Yes,
is for direction. Yes.
SI unit of a momentum is kg meters kg
Meter per second
meter per second or
or
kg
meter second inverse.
meter second inverse.
Fine. Good.
CGS unit of momentum is gram
Gram
centimeter per
per
second
second.
gram centimeter second inverse.
Yes. Yes. Now this is clear. This slide,
Yes,
what you understand. See, I that's why I took purposely the next slide. Now things are quite clear. Ninth standard. Ninth standard, boys.
yes, ma'am.
Yes. Have you understood? I took two slides for momentum. Have you understood nicely?
Yes, ma'am.
All of you?
Yes.
Okay. Now we have finished Newton's first law of motion, momentum, and now we are going to work on Newton's second law of motion. Please begin, Beta. Please start. What happened? Can you hear me? Hello? 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 Can you hear me, Beta? Hello? Hello? Hello?
Yes, ma'am.
Yes, can you hear me?
Yes.
Okay. I had to restart because I did not get any voice from your side. Okay, please start reading then.
Number 8. Newton's second law of motion. Newton.
Who is reading?
Newton's second.
Who was reading earlier?
Me, ma'am.
Start.
Newton's second law of motion. Newton's second law of motion states that the rate of change of momentum of an object is proportional to the applied force in the direction of force.
So what are we talking about? We are talking about direction and the application of force, both. So what it says, the rate of change of momentum is proportional to the force and the direction of the force, right? Yes? Now we will see the mathematical formulation of second law of motion. Please begin.
Mathematical formulation of second law of motion. If an object of mass m is moving along a straight line with initial velocity u and is accelerated to velocity v in time t by applying a force F, then initial
Just a moment,
momentum.
just a moment, beta. Now this is the body. This is a body, right? This is having mass m, right? It is moving in a straight line. It is moving in a straight line. Initial velocity is u. When it goes to a certain distance, its velocity becomes v. How much time is been taken? T. And what force is applied? F. This much have you understood? This you have understood or not? Now the object is over here. Have you understood this much?
Yes, ma'am.
Yes? All of you? If you don't understand, you will not understand this mathematical notations. This much have you understood what I showed you just now? Boys, can you hear me?
Yes, ma'am.
Fine. So what is initial momentum, beta? What we have said P is equal to mv, right? So the initial momentum will be P1 is equal to mu. Why we have taken u? Because this is the initial velocity, right? Hello, do you understand? And the final momentum will be this v. P2 is equal to mv. Understood, all of you? So one momentum we find over here and the other momentum we find over here. Okay, so initial momentum is equal to mv and final momentum is equal to mv. Have you understood this much? Abdul? Hello?
Yes, ma'am.
Yes. Have you understood this two lines?
Yeah, ma'am.
Okay. Continue. Please continue.
From where, ma'am?
From change in momentum.
Okay, ma'am. Change in momentum P square.
No, it is P2.
P2, sorry, ma'am. P2 minus P1 is equal to MV minus MU.
What is P2? MV. What is P1? MV. So what we did change. So whenever you are working with change, we have to find difference. Remember? Whenever we
Yes,
are trying to find a change, that means we have to find the difference. We have to subtract from the final. The initial has to be subtracted from the final. You know that, right?
yeah, ma'am.
Okay. So
M
MV minus MU. Fine.
MV minus MU is equal to M in bracket V
No, no, no.
minus U.
Just a moment. Now you have to come to rate of change of momentum. Please understand what I'm trying to say. Now you have to come to rate of change of momentum. Whenever we talk about rate, we have to divide it by t, isn't it?
Yeah, ma'am.
Okay. So what do you have
Rate
to
of,
find out? Huh,
rate of change of momentum is equal to M in bracket V minus U divided by T.
t. Right.
We
Absolutely
can
right.
we can say divided by T, no, ma'am.
Yes, you can say divided by t. No problem. Yes. We have to understand. We say this way or that way does not make any difference. We
Yeah.
should understand. That's it. Okay. Now the applied force
For the applied force F A
directly
M
proportional. No, it is directly proportional.
directly proportional M V minus U upon T or
Yes.
F is equal to K
A.
M V minus U upon T, but V minus U upon T is equal to A.
Okay. This much have you understood or not? Or should I explain? Should I explain? Hello. Should I explain, Vita?
Yeah, ma'am.
Okay. Fine. Fine. No, no problem. Now, this much have you understood? Rate of change of momentum.
Yes, ma'am.
Okay.
Yes.
mv minus u upon 2 you have understood, right? Now, force is directly proportional to mv minus u upon 2. This much you are okay? This is what we had started with. That force is directly proportional to momentum. Yes or no? Mass and velocity. Yes or no? Momentum is a type of force. Yes? When we remove this proportional sign, we get K. So it becomes equal to and K. I told you earlier that we put a constant sign. Yes? Do you remember? That when we are changing the proportional sign to equal sign, we put a constant sign. Do you remember? Can you hear me?
Yes, ma'am.
Okay. So instead of proportional sign we have put equal to. And as soon as we put equal, we have to put a constant sign that is k. Yes? And the rest remains the same. mv minus u2 upon t remains the same. Is it clear? Is it
Yes,
okay?
ma'am. Yeah, ma'am.
Okay.
Okay.
But we also know that change in velocity is acceleration. Yes or no? That
Yes,
we
ma'am.
learned earlier. Okay. So instead of v minus u upon t, what we'll put? A. So F is equal to, now look over here. We will take only this. So F is equal to K, K, M, and instead of V minus U upon T, we are writing A. So now the equation becomes F is equal to KMA. Is it fine with you? This is a new formula that we observed. Now, where k is constant of proportionality, so we will remove k and it becomes F is equal to ma. This is your formula. So, what is force? Force is the product of mass and acceleration. So, we got a new formula altogether. Yes? Boys, are you understanding?
Yes, ma'am.
Yes. Now, read the SI unit. So,
Okay.
as simple as
So the
that,
SI
what
unit
is, what
of
is, yes, what is mass? Kilogram, right? What is
kilogram,
mass?
yeah.
Kilogram.
Kilogram
What is acceleration? Meter per second
second
square.
square.
Remember? Yeah,
Yeah.
simple. So what is written? It is Newton. So simple it becomes. So kilogram meter per second square is equal to Newton. So we also know, I think you are aware of what is Newton.
Yeah, ma'am.
Yes, fine. So please
So
read
the
out.
SI unit of mass is kg and the acceleration is
Meter,
meter
meter per
per second
second square.
square. So the unit of force is kilogram meter per second square or Newton. It is
Okay.
it is its
Its
symbol
symbol.
is N.
So you are through. Any doubt regarding this slide? Do you have any doubt regarding this slide?
No, ma'am. No, ma'am.
All of you have understood nicely?
Yes, ma'am.
It's the same thing. Can you read it once, better, if possible?
What, ma'am?
Please read it once.
Yeah. Newton's second law of motion. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Force A change in momentum upon
So
time
you are,
taken.
just a moment, just a moment. What is the sign? You have to say this force is directly proportional to. Isn't that force is proportional to? You have to say like that. Force is proportional to,
Force is proportional to change in momentum upon time taken.
so F is proportional to, please read.
Ma'am, I can't see the clear screen, ma'am.
You can't see.
Screen, yeah. I can't see. Wait, ma'am. I
Okay.
think some
Delta P.
network issue.
Okay, F is proportional to delta P upon T. This you can understand now if I'm reading it out. Delta P is the difference of the momentum. So F is proportional to mv minus mu upon T. F is proportional to m v minus u upon T. F is proportional to m because v minus u upon T is equal to A. So F is proportional to m into A. F is equal to KMA. Now can you read? A force of 1 Newton applied on a body of mass 1 kg produces an acceleration of 1 meter per second square on the body. Then 1 is equal to k into 1 or k is equal to 1. So therefore F is equal to m into A. And we know that force is equal to mass into acceleration. So we come to a conclusion. The same slide that we had done earlier has been done again, sort of revision. You understood now? It's the same slide, but in a different manner. Hello? Hello? Now, can you see the slide? Can you see the slide?
Yes, ma'am.
Who is it?
Yes, ma'am.
You can see the slide. What had happened to Shahim? I don't know. He said he is not able to see the slide. So I think we are through the session. It's time up. I think we have already taken 1 minute, more of 1 minute. So I hope you have understood regarding the momentum. So today's topic was momentum and the second law